Hey everybody, welcome to today's discussion on the history of the atom. As you can see from your screen, it's going to be history of the atom part 1. Uh, this entire unit that we're about to start is a deep dive into how we got from what we thought was the beginning of, or what we thought was the atom at the beginning to our most current model of the atom. Now, before we can dive into what our most current model is, we have to go through many iterations of what we thought the atom was. And why I like this unit is because it proves that science is always right until proven otherwise, which happens often. So I like to say or joke that all of these older scientists that had worked on the atom, right, they were actually wrong, but we had to believe them because that's what we knew at the time. And they shouldn't be embarrassed for being wrong. That's just the best of what we had currently available. So it's kind of like I say to you guys in class, it's okay to be wrong as long as we learn from our error and learn from those mistakes. Now, I want to dive in way back in BC era, right, with our very first person who came up with the atom, and that was one of our ancient Greek philosophers. Now, I'm sure you've heard of the ancient Greek philosophers, right? They're known for their ability to debate and to argue and to come up with all these great ideas and ideals. And Democritus, who's one of the probably, I wouldn't say less known, but definitely not the one that not the first one that pops to my mind. Democritus, also known as the laughing philosopher because of his joy, was our first person who kind of gave us an atomic theory. And Democritus actually states that atoms are the smallest form of matter and that they are considered indivisible. Okay, so they're considered indivisible, and everything on this earth is made of atoms. And what's beautiful about this is that we're going to circle back to this in a later atomic theory, but this actually came from the Greek word atomos, which literally means indivisible. Now, unfortunately for us and the scientific community and whoever else, right, Democritus's theory didn't last very long. Again, ancient Greeks were kind of built on this idea of being able to argue and defend their theories, and they kind of built up a following, if you will. And unfortunately, Democritus's following was much smaller than the following of another prominent philosopher who goes by the name of Aristotle. Now, Aristotle disagreed with Democritus, and Aristotle actually believed that the Earth was entirely made, or I'm sorry, that everything we have is made of 4 different elements: earth, okay, wind, fire, and water. And because Aristotle had a much larger following, Democritus's opinion of the atoms kind of fell off and was no longer really considered the theory that we wanted to follow. Now, we're talking about 400 BC as our time period for Democritus and Aristotle, like a very long time ago. So you might think to yourself, okay, well, maybe, sometime in the early AD era, we came up with an idea of the atom. But interestingly enough, our next theory of the atom didn't come around until around the year 1800. Okay, I think around the year 1804, an English scientist by the name of John Dalton decided to propose an atomic theory. Now, his atomic theory was based off of what we call postulates, or different statements about what his theory was based on. Okay, and so the first postulate of his theory was that atoms are the smallest form of matter and that they are indivisible. Okay, so that should sound really familiar to you because, hey, thanks Democritus for that theory. John Dalton's also going to use that in his theory. He believes the same thing. Atoms were the smallest form of matter. They're indivisible, okay, and everything is made of atoms. The second postulate to his theory stated that atoms of the same element are identical. So atoms of the same element are identical. So what does that mean? That means that atoms, as long as they are the same type of element, so let's say I have 30 atoms of carbon, each atom of carbon is the same, meaning it has the same properties, the same mass, and the same size, okay? His third statement in this was that atoms of different elements, so atoms of different elements are different, okay? And that sounds kind of silly to say out loud, but what that means is that while all of our atoms of carbon are identical to one another, if I were to take an atom of carbon and an atom of nitrogen and compare them to one another, they are going to have different properties, different masses, and different sizes, okay? And another portion of his theory was that atoms combine in whole number ratios. Now, this should also sound familiar to you based on our discussion of compounds, right? A compound is always going to form in that same definite proportion, and that was thanks to John Dalton that we kind of have that theory. And the last component of it is that atoms can rearrange, combine, or separate during a chemical reaction, okay? So that's during a reaction. Now, these 5 postulates are, again, the basis of John Dalton's theory. And for each of our scientists, we like to give them a nickname for what their theory was called. Now, John Dalton's theory is lovingly nicknamed the billiard ball model. Okay, so the billiard ball model. And if you're not familiar with what billiard is, remember that most of these scientists are going to be English or European, and billiards is the same thing as shooting pool. So if you've ever played pool, you know that one with all the hard balls, the 8-ball, okay, that's a billiard. And so this kind of describes what we should sketch his model of the atom like, which is a solid, hard, round sphere that cannot be divided. It is the simplest form of matter. Okay, so that's John Dalton. And John Dalton's theory was relevant for probably, I want to say, almost close to 100 years, because it wasn't until 1897 when we had another English scientist or philosopher, or not philosopher, physicist, I'm sorry, whose name was J.J. Thomson, which sounds like Thompson, but it's actually Thomson with no P. And in 1897, J.J. Thomson was playing around with a cathode ray tube. Okay, a cathode ray tube. Now, in this assignment on Google Classroom, I'm going to post a video of what a cathode ray tube looks like in real time. But for the purpose of today's recording, I am going to actually just insert an image. And if you're following along on my guided notes sheets, this image is already pasted there for you. So this is our cathode ray tube. It looks really complex, and there are some words here that you might not be familiar with, like cathode or anode, but the basis of the cathode ray tube is that it is going to be this vacuumed out tube, meaning they've removed any impurities of the air, and they filled it with an inert gas, meaning a gas that's not going to react at all, okay? And so what he did is he decided to to have a high voltage electrical current applied to the end of these plates. So what ends up happening is that a cathode ray will travel from the cathode to the anode, okay? So again, without the video, this is a little bit hard to see, but essentially when he flips this on, what we end up seeing is this beam that comes from the cathode and travels to the anode, okay? Now you can see the electron beam shoots all the way through, and we have a fluorescent screen to kind of measure where that beam is hitting, okay? Now, what people, the main questions that people kind of had about this were, is it just a ray of energy that travels in waves like light? That was really popular. Or is it a stream of moving particles? That was also really popular kind of theory of what was happening. And so Thomson decided that he wanted to test these ideas by applying a positive and negative plate to see what happened when that magnet was applied to that beam to see kind of what that beam was actually really made of. Now, interestingly, and I'm going to use different colors to show you this, okay? Let's say he applied a positive beam or a positive magnet to that beam. What he noticed was that when he applied that positive magnet, the beam of light, instead of traveling straight through the cathode ray tube, bent upward towards that positive plate. Okay. He then decided to test, well, what happens then if I instead apply a negative, and I'm going to use yellow for negative. What happens when I instead apply that negative plate? And what they noticed, or what he noticed, was that that beam of light, instead of bending towards it, it actually repels away. Okay, so it bent the other direction. So what does he conclude from this? Well, if we think about what we know about the atom, we should be able to very easily come up with this idea of, well, what do we know about charge? When we apply a positive charge to a negative charge, they attract, right? We've been taught that our whole lives, opposites attract. And when we apply a negative to a negative, it repels, or when we apply a positive to a positive, it repels. But so what he was able to conclude, was that since this negative that was applied caused the beam to repel, he concludes that there must be negatively charged particles, okay, within this matter. Okay, now what's crazy about this is that if you think back again to what Dalton said that matter, an atom was the smallest form of matter, it couldn't be subdivided, and so there was nothing else but just that atom. So here we are almost 100 years later, and we're already disproving John Dalton's theory by J.J. Thomson discovering our subatomic particle, the electron, right? And electrons, okay, have a negative charge, okay, and they are very, very teeny tiny. And we're going to talk about how he figured that out also, okay? But he did figure out that it wasn't just energy and that it did have some mass, okay? And the way he was able to determine that it had some mass was by looking at the mass to charge ratio, okay? And what he discovered by looking at that mass to charge ratio, because initially the thought was, well, could this just be just a negative energy that's here? And is there any mass to that, which is what would make it be considered matter? Because remember, we defined matter as anything that takes up space and has mass. So he was interested in finding out, is the electron considered matter? Right? And so he did this by kind of determining how much the cathode rays bent when he varied the voltage, okay? And again, the mass to charge ratio. And what he found is that it was 1/2000th the size, okay, of the smallest already known piece of matter, which was the hydrogen atom. Okay, so he found it was 1/2000th the size of the hydrogen atom, which led him to really think that this was another particle. Okay, so Thomson then inferred from his discovery that electrons are fundamental particles that are within the atom. So what did he nickname, or what did we nickname his model? His model is nicknamed the plum pudding model, which again is a British dessert. Okay, but I like to call it the chocolate chip cookie model, because what his model was a bunch of negative electrons embedded into a positive sphere, because he did know that atoms were neutral, but he now had to somehow place those negative particles within that atom. All right, everybody, have a great day, and I'll see you next time.